So, good morning, everyone. We are trying to understand black body radiation and its importance. So, just to initiate the topic, we can estimate the temperature of a given body by looking at the radiation pattern. So, for example, for a lava, looking at the wavelength emitted, we can estimate the temperature of the lava. We'll be using few terms like total energy density, spectral energy density, emissive power, and you can go through these definitions as you proceed. Now, the term that we are using again and again is a black body. So, let's understand what is a black body. A black body is supposed to be a perfect emitter and a perfect absorber of radiation. It is an ideal body which at lower temperatures will absorb all possible radiation, which means all possible wavelengths, and at higher temperature it will emit all possible radiation. And this black body radiation spectrum is an experimental observation, and for long time it remained a puzzle in the sense that it was very difficult to explain the kind of spectrum one gets whenever one looks at the black body radiation spectrum. So, defining black body once again, a body that absorbs all radiation incident upon it, regardless of the wavelength or frequency, is called a black body. And being a perfect absorber, it is equally a perfect emitter or a radiator, which means at a higher temperature it will radiate all possible radiation. So, since it's an ideal concept, experimentally, when we look at a black body, we look at a cavity with a little opening into it, and the inside of the cavity is perfectly reflecting, so that any radiation that enters through that small opening is multiple times reflected inside this black body, and the radiation is not allowed to leave out. So, for example, if some radiation enters from here, then that radiation that enters from here will remain within this. So, for example, if we choose some radiation and we allow that radiation to enter through this opening, once entered, it will be multiple times reflected and it will never leave the system. So the radiation remains inside, and therefore it is said to be a perfect absorber. This is how we experimentally look at a black body. Moving ahead, if we look at the spectrum of the spectrum of the black body is a very typical spectrum which is shown over here. And you can see that at different temperatures, the curve acquires a different shape, and the maximum wavelength that is observed takes a shift towards the lower value as the temperature increases. This was explained by Wien in the form of Wien's displacement law, which is given as lambda max, the maximum wavelength, multiplied by the temperature is equal to a constant which is known as Wien's constant. This constant Hc upon 4.965 K is replaced by a value B, which is known as Wien's constant. The amount of energy radiated is given by Stephen's law, which is equal to the total energy E is proportional to T to the power 4, which can be written as E is equal to sigma T to the power 4. So, looking at the Stephen's law gives the total amount of energy radiated, which is sigma T to the power 4. This law is valid for any black body, and for any other body other than the black body, the temperature variation would slightly change, or the slope of the line will slightly change. So, with this, now let's understand how this black body radiation spectrum became the biggest puzzle of that time. During that time, it was the classical theory which was prevalent. So, with the classical theory, looking at this, people were looking forward to explain this typical pattern of the black body spectrum, where it rises for a certain wavelength range and then it shows a decrement, and that too with a long exponential tail. If you look at this graph carefully, this graph rises with the wavelengths initially and then it drops down exponentially. So, this radiation curve was explanation to this radiation curve was an unsolved puzzle during that point of time. So, if you typically look at the black body radiation curve, what is it indicating? Let's understand that the black body radiates energy of all wavelengths, starting from 0 to maximum value. The energy of the radiation initially increases, reaches to a maximum wavelength, and then it decreases and it continues to decrease, never going to zero. At around 5000 Kelvin, the peak wavelength is about 500 nanometers, and this is typically shown for sun, which has a surface temperature of around 5800 Kelvin. So if you look at the sun spectrum goes like this. At each temperature, the black body emits a standard amount of energy, which is represented by the area under the curve and is mentioned by the Stephen's law, where E is proportional to T to the power 4. As the temperature increases, the peak wavelength emitted by the black body decreases, and this is represented by Wien's displacement law. Now, people tried to explain it using the classical theories, but the classical theories didn't work. So, one of the attempts to explain the black body radiation behavior was by Rayleigh jeans in the form of a Rayleigh jeans law, which is mentioned over here in terms of the formula. If you look at this formula could only explain for low frequency values. That means for higher wavelengths, Rayleigh jeans could match the curve. The supposed curve of the black body radiation could be matched with Rayleigh jeans law. If you look at this portion of the curve, the Rayleigh jeans law could fit in over here, but it continues to increase as the wavelength was decreasing or the frequency was increasing, and that is termed as the ultraviolet catastrophe. That means ultimately that formula merges to an infinite value of intensity, which never happens in case of a black body. For a black body, it goes as an exponential region, but then it shows a sharp dip if you observe it carefully. So this was not explained by the Rayleigh jeans law. So this is the Rayleigh jeans law which is mentioned over here, and this Rayleigh jeans law could only explain one part of the graph. So this Rayleigh jeans law was entirely based on the classical approach, where using the wave theory we tried to understand the black body radiation. The Rayleigh jeans law given as 8 pi nu cube by c cube into kBt, where k is your Boltzmann's constant. Further, what Rayleigh jeans formula tried to mention, right? Just pay attention that over here now there is frequency instead of the wavelength. The earlier graphs were showing wavelength at the x-axis. Now there's a shift. Now we are representing it in terms of frequency. So it is fitting for this low frequency range. For wavelengths, it is the higher wavelength end. For frequency, it's the low frequency range. So the curve agrees at the lower frequency range but immediately starts deviating as the frequency increases. So, this discrepancy between the theory and the experiment is known as the ultraviolet catastrophe, where the classical value reaches to a very high value ranging to infinity, while the actual value takes a sharp turn and starts showing a different kind of a behavior. That is what we can see. So, with this Rayleigh gene, again, Wayne tried to give another explanation. So, he modified the formulas and he tried to explain it in terms of an exponential decay. Now, the Wayne's curve could not explain for the lower frequencies, he could only explain for the higher frequencies, that is the lower side of the wavelength. So, if you look at the Wayne's law, the Wayne's law is an exponential law which could only explain for higher frequencies. So, the Wien curve could match for the higher frequencies, while the Rayleigh Jean's law could only fit in for the lower frequency ranges. And one complete law to explain the whole curve was not available using the classical approach, where these molecules were treated by taking into account the kinetic theory of gases. The kinetic theory of gases, which you have read in your previous classes. Then came the Planck's hypothesis, where the Planck's hypothesis was based on quantum postulates, where the blackbody radiation chamber was considered to be a collection of simple harmonic oscillators or resonators, which were also called these energy emitters, which were of the molecular dimensions. So these Planck oscillators or Planck resonators were allowed to vibrate with all possible frequencies, and they were in a quantized state, which means that the energy was only integral multiple of h nu. This is something which was introduced by Planck, where Planck said that these oscillators can only absorb and radiate energy in the form of these packets, which were called quanta at that point of time, and later on mentioned with the name photons. So, using Planck's theory, Planck combined Rayleigh Jean's approach as well as Wien's approach, and using a different approach where the energy levels were incorporated, he could come up with Planck's radiation law. We are not going to discuss the derivation. So, straightforward, we are looking at the formula, and this formula had an exponential approach on one side, and when we talked about the lower frequencies, it merged with the Rayleigh Jean's law. This is termed as the Planck's radiation law in terms of frequency, where we are describing the total energy or the spectral energy density u nu du nu as 8 pi h nu cube by c cube 1 upon e raised to the power h nu by kbt minus 1. This is the total energy density. So this equation could now completely describe the whole curve. That is how the black body is described. So now what we have to understand clearly is that the classical approach was based on considering these molecules as moving in the form of waves, and the standing wave pattern was considered, and the average energy per mode was considered to be equal to kBt, the Boltzmann constant, into the temperature. While in the quantum approach, the energy exchange was only in the possibility of quantized modes, which were multiples of h nu. So the average energy per mode in that case was estimated to be h nu by e raised to the power h nu by kt minus 1. And it helped to explain the full spectrum. So by Planck's law, it could fit in both the Rayleigh Jean's law as well as the Wien's law. For both the ranges, it could explain clearly. So the same Planck's law for high frequencies matches with the Wien's law, and for low frequencies matches with the Rayleigh-Jeans law. We can just check that for low frequency region, this is important for you all to note that the same law, the Planck's law, can reduce for low frequency regions. If we take this approximation that h nu is much, much less than kt, then we can approximate this exponential term to be much less than 1. And therefore, our expression reduces to Rayleigh-Jeans law. While for high frequency region, h nu is much, much greater than kt. So e raised to the power h nu by kt is much, much greater than 1. This is important to understand. So this whole term can be approximated as e raised to the power h nu by kt. So the same law, that's the Planck's law, reduces to Wien's law. Just remember carefully, this is the Rayleigh-Jeans law from Planck's law, which we have obtained. And this is the Rayleigh-Jeans law. Just see. This is in the low frequency region. And the other one is the Wien's law, which is in the high frequency region. So both the Rayleigh-Jeans law and the Wien's law can be obtained by making use of the Planck's radiation law. We talked about Wien's displacement law. The Wien's displacement law is simply maximum wavelength into temperature is equal to a constant, which is denoted by this constant B. This is referred to as B. This whole constant is termed as the Wien's constant B, which has a value of 2.898 into 10 raised to power minus 3 meter Kelvin, which is a constant. So if you know the maximum wavelength emitted, you can estimate the temperature. And if you know the temperature, you can estimate the maximum wavelength limited. This law is known as Wien's displacement law, which is different from the previous law. The previous law is Wien's law, which is explaining the radiation curve. Wien's displacement law is giving you an account of the maximum wavelength that is emitted. So if you are aware of the maximum wavelength, the temperature can very easily be estimated as lambda max into T is equal to B. So T is equal to B by lambda max. We can easily use this formula to estimate the temperature of a given surface if we are aware of the maximum wavelength emitted in the blackbody radiation spectrum. This is the maximum wavelength. I hope you can understand what I'm talking about. Numericals related to this can be easily answered. Similarly, we talked about the Stefan's law. The Stephens-Boltzmann law is a modification of it. This talks about the total energy density. And the Stephens-Boltzmann law is known as E is equal to the emissivity into sigma T to the power 4, where the Stefan's constant is given as 5.67 into 10 raised to power minus 8 watt per meter square Kelvin to the power 4. So with this, we have ended the discussion of radiation, and I hope you can solve the numericals related to this. So thank you, everyone.